So in the last video, I spoke about how Spotify used agentic systems or large language models to improve the query understanding part of the system, where it kind of like it helped the search engine to understand what the user is mentioning, and then use large language model as a router. So basically, to route to the right tool or kind of like the right model to address the query. So it also, I think, what I can put it up is like it kind of like helped the search engine to do in three main aspects of it. One is called what we call as query expansion. Like given a query, if I want movies related to Titanic, it kind of like you can expand the query telling that okay, movies related to Titanic include a lot of romantic movies as well as like it includes a ship and like in water. It's a kind of like a drama kind of a movie. So you're expanding the query and adding more information to the query. The second part is query rewriting. So sometimes when you kind of like write a query to Spotify telling that I want um, a recent album by Bruno Mars. By mistake, if you had written album, maybe there's a written recent song, not an album. So it kind of like can help you in writing this query multiple times again and it the vector database to search the relevant items. So it can write you three things. One is recent songs of Bruno Mars, recent albums of Bruno Mars, and recent singles of Bruno Mars. So it kind of like rewriting the query in different ways. So we spoke about query expansion, query rewriting, and third one is facet extraction. So what we talk about facet extraction is basically given a user query, we kind of like find the relevant important keywords. One is again relevant like recent album by Bruno Mars. Album is one of the facet, a keyword which can help the query to understand a lot more better. And these facets can be used as parameterized parameters for the subsequent models like the tools or subagents or machine learning or AI models to run and give output back to the user. So it's kind of like getting more parameters out of the query. So that 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 is a very powerful technique of like making understanding the user query and kind of like helping add more relevant information. So now there's another research paper on the similar lines, but on a different way. They're using large language models, but it's more of like how so Netflix is using LLM reasoning for especially cold start recommendations. So we have heard about cold start for a good amount of time right now, starting from 1990s of like collaborative filtering to the recent two tower models where and using embeddings and all of that to kind of like address cold start recommendations. But in the recent times, there have been models like wide and deep networks where we hopefully figure out the way of the user interactions, the past user interactions, and the cold start items kind of like captures the right patterns and features in the embeddings, so that we're kind of like taking a bet that the embeddings capture all the relevant features like the patterns of a user or an item, so that when given a very new item, it kind of figures out that okay, this can be a relevant item for this particular user. It can be an item or a movie or a product on Amazon or Walmart or even songs as well. So we take a big bet on those embeddings. So these embeddings are usually generated from semantic IDs, like kind of like the title of the song or a product, or coming to metadata of these items. Coming to products on Walmart or Amazon, it's more of like what department, category, what is the color of the product, and what is the brand of the product, and description of the product, and all that. Coming to movies on Netflix, it's more of like what genre they come in there, and what kind of the cast of the movies, and they kind of like it also talks about the mood of the movies, like is it like low or is it like an happy ending and all of that. And it also talks about where it is shot. Like if you see a lot of movies are shot in certain countries, which has more propensity for user to watch those particular movies. And these are the certain metadata which can help the embeddings of these movies to capture intrinsically. And if you come to songs, it's more again similar to movies. It's more of like who's the singer and who's the composer, who's the lyricist, and kind of like what kind is it rock, pop, jazz, etc. So all of these given, they kind of like create embeddings for each of these, like maybe a product name, or maybe for every product you have item embedding. Maybe for movies you have like movie embeddings for every movie, and for like songs you have like embeddings for songs. And we take a bet that these embeddings capture the fine grained patterns of different of these characteristics of that particular items. So but this is another way of looking at it. So with the large language models having world knowledge, and kind of like what we have seen before, it has helped to expand the understanding of queries. So we hope so that this will help expanding the understanding of different items, movies or songs as such. So, but coming to Netflix, I'll be taking the example of Netflix, and so I'll be focusing all my examples towards movies in this particular paper. So, so what they talk about here is they're trying to like um, large language models. So large language models, let me just, I've shown significant I've shown significant potential for improving recommendation through their inherent reasoning capabilities and extensive knowledge base. This about. So they're addressing cold start scenarios. So this utilizes the LLM's reasoning capabilities to efficiently infer user preferences. So that's what we spoke about. Um, LLMs which is equipped with extensive world knowledge and reasoning capabilities are well positioned to address this. So let's go directly to, we know that they're using LLMs for cold start. What are they trying to achieve? So specifically, they're telling that they'll take cold start items which are launched after the so they're basically targeting cold start items, and they're going to take a latest LLM model which the latest interaction of all user historical transactions. So they're going to take items which are released after the release of an LLM model. For example, if you see GPT-4, GPT-5, you have model versions. That tells you that the date until which the model has been trained until. So anything after that, the model would not understand. Like any news in the world after that particular model version, it would not understand. So they're telling they're going to take all the items after the model version because they don't want to cause any data leakage from the LLM models to the cold start items when they're training their model. So also the launch of cold start items is later than the training time of the base LLMs we used. And also they're also telling that the latest interaction, so they're going to take items after the latest interaction, maybe like if the training data is until like end of this year, so they're going to take all the cold start all the items launched after January of 2026. So they are mentioning that they're going to evaluate all methods on the re-ranking task. So they're not working on the what do you say, retrieval layer. They're morely working on the re-ranking stage where 100,000 to millions is been like in the database. Then you kind of like retrieve around like 100,000 to thousands of candidates, and then you re-rank these thousands of candidates into like just top 10 or top 100 to top 200. So they're working on the re-ranking stage rather than retrieval stage. So specifically, we select the top 40 titles from the ranking model used in the production environment at Netflix. So they're taking the top 40. We then further sample 10 cold start titles, including the target title, to form a total of 50 candidates. So they're reaching to the production environment for a given, I think, user. They're kind of like taking the top 40, like the top 40 candidates, and then they're just like putting the top 10, like kind of like randomly sample 10 cold start titles from the database. Maybe they can improve by like the same as retrieval. They can find the most nearest for the user. They can like, okay, the user's embeddings to all the cold start titles. You figure out, okay, maybe the top 10, and then put it into the ranking layer, so that then we can re-rank it with all the 50 titles. So the final task is to re-rank these candidates for recommendation. So it is basically the top 50 candidates now, which has to be re-ranked using the approach mentioned in the paper. So when you look at the approach, what is mentioned here, so we're just going to start about how the reasoning happens for the recommendations. So the paper mentions two approaches. One is called the structured reasoning, and another a variant of the self-consistency approach. So these approaches, I think they're used to design or decompose users' interaction history into multiple reasoning paths, so enabling a more accurate analysis of user preferences. So these two strategies, what they mentioned, they're used to decompose users' interaction history of the whole historical interactions into multiple reasoning paths, or like finding patterns out of it. Like maybe given a user sees a lot of movies related to, or a user can see a lot of movies related to sci-fi, or a particular director or a particular actor. So these are the different reasoning paths or patterns found from, I think, by using LLM for large language models. So let's deep dive into what's happening in these two approaches. So structured reasoning, we want to systematically decompose structured information from a user's interaction history. So evaluates compatibility between each path and the candidate by computing match scores. This enables LLM to recommend items with the highest overall score. This is the overall approach, but let's start diving into deep dive into the more granular parts. So the reasoning paths construction. So we first construct a graph of reasoning paths from the user's viewing history. And then we construct the three reasoning paths based on the user's preferred actors, movie genres, and directors. In the structured reasoning path, we kind of like give a static or a kind of like reasoning path which has to derive patterns out of it. For example, I want to given a user's historical interactions, I want to see if there's any derived pattern on actors. I want to see any derived patterns on directors or any derived patterns on genres. So when I give these three factors, it kind of LLMs can go in to see every movie and see if there's any pattern of any particular actor or any particular director and all of that. So but I'm kind of like giving a static factor or reasoning path for the LLM to figure out. So that's what this is the reasoning paths construction. And uh, during inference, we prompt the LLM to identify the most significant factors influencing the user current preferences, then construct a reason for each factor by sequentially extracting relevant events from the universe. So using the relevant events, maybe like the user is seeing a lot of sci-fi movies. So out of 100 historical interactions, maybe around 50 to 50 historical actions or events, maybe towards sci-fi. So kind of like the large language model figures out that. Then the next part is once you figure out these, the next part is factor match calculation. So you kind of like the LLMs gives out, okay, the if you see the upper workflow here. So if you see here, a user is kind of like a user has three reasoning paths. Maybe this is like the this like which is the cast in the movie, and second one is the genre, and the third one is like a particular director. So then the LLM figures out, okay, the user sees a lot of movies starring Anna. The second one is a lot of horror movies. Third one is a lot of movies related to the director David. So kind of there are three patterns which is found out, and then you figure out each of these factor, how much of it is relevant given a candidate. So they're talking about factor match. Second, for each candidate item, we construct the LM to compute a match score with respect to each constructed reasoning path. So, given a candidate item, we saw this 50 candidates, right? For every candidate item, find out if how much of the factors or these things related to them. So, for example, the new candidate here is an action movie starring Anna, directed by Tom. So, this is like the new candidate, and the first one, all starring Anna, has a lot of similarity towards this candidate, so it gets zero point 0.9. And all horror movies, so since this is an action movie, this will have very little relevance, so it's 0.1. And all directed by David, since it's directed by Tom, it will have very less reference. So this is the factor match. So this is how the factor match is calculated. Now coming to importance, weights, and aggregation, we need to somehow aggregate and also give certain importance and get other metrics into the weightages. So what they're doing here is importance weights to each reasoning path as factor prominence. How much is the factor prominent in this particular candidate, action type, and recency. So how recent was these actions taken place? So this could have been like 5-6 months before, but more recent makes builds more confident in the recommendation algorithm. So these three were taken care, and these three factors were taken care and added an extra weighting towards these. So if you see here, a zero point 0.8 for the all starring Anna, and 0.2 and 0.3. Maybe this add less relevance, but a lot more on these three factors. So this is another kind of a factor added into the implicitly into the approach. And this weighted kind of like numbers is used to get the final score, and then ranking of these scores gives the final candidate ranks. So this is the structured approach where, again, to summarize quickly, so basically they're giving static reasoning paths, and the LLMs figures out a patterns of these reasoning paths, like directors, actors, and genres, and figures out a pattern. Okay, a lot of movies by this particular director, this particular actor, and this thing. And then you kind of like give a max score for this each of these factors for all the candidate list, and then you kind of like give another weighted part of it by including other factors into it, like recency, factor prominence, etc. And then you kind of like find the final score to get the recommendations. Now the second part is called soft self consistency. So the structured path was like you add a structured way of like figuring out the reasoning path. Now soft self consistency is kind of like an approach where we generate multiple parallel reasoning paths and aggregate them for final recommendation. You're kind of like leaving the language models to loose. You figure out all the different reasoning paths and give it to me. And but once you figure out all the reasoning paths, you use kind of like a voting mechanism. LLM autonomously construct diverse reasoning paths, employing the classic self-consistency method and a strict majority voting mechanism. So you kind of like give me those reasoning paths which have when you have generated, half of the time it's coming out as the same. For example, if I generate 20 reasoning paths, then like LLMs looking at the past user history. So many a time, like, okay, actors, particular reasoning path, like movies related to actor, maybe like um, DiCaprio is coming out more than 10 number of times for 20 reasoning paths. That means it's a very prominent reasoning path. So this is the self-consistency method using language models. But usually this has to happen at least half the number of times you generate the reason. Because basically we generated 20 times, 20 reasoning paths. Then the movies by DiCaprio should at least happen more than half, which is 10 reasoning paths. So this is really difficult, and like with the amount of variance in the data and the amount of variance in the language models, it's very difficult to figure out reasoning paths. So they went to a soft summarization strategy. What they do is basically, instead of giving a threshold of half number of times n by 2, they kind of go with like the highest frequent reasoning path. Out of the 20 reasoning paths, maybe like DiCaprio happened 5 times. Then that would be the most relevant reasoning part. So they use this kind of like soft summarization strategy. Then it is noteworthy that Russell's approach can be viewed as a simplest variant. This is a lot more simpler variant than the structured reasoning, because in structured reasoning you kind of like have three different stages of getting the recommendation or the re-ranking. Structured explicitly instructs the LLMs to construct reasoning path by extracting historical events by clearly identified preference factors, by clearly identifying preference like director, actor, and like genre. But soft self-consistency approach delegates both the construction of reasoning paths and the summarization of recommendation entirely to the LLM itself. So it's like it's given use. So anything the LLM can generate as reasoning paths, and then it automatically votes by like which is the maximum frequent reasoning path given a user's history. Now they're talking about in this paper, after developing these like reasoning strategies, they want to further investigate like the effectiveness of like fine tuning this particular LLM, either using like a supervised fine tuning or a reinforcement learning kind of an approach, and as well as like using the combination of both SFT and reinforcement learning to like increase the efficiency of the reasoning paths generation. So one particular part, the first thing they're trying to do is the supervised fine tuning, where if you see here, they're trying to enhance the performance by learning from high quality next sentence prediction, next token prediction trajectories. So in this, they're trying to like define reasoning paths that lead to successful user preference prediction as exemplary patterns for the model to emulate. So they kind of like from the past two approaches, one is the structured reasoning path and the second one is the self-consistency approach. From either of these approaches, they're trying to find some of these examples which led to a good successful user preference prediction. So leading to a successful prediction, using those as the good examples, they're trying to use that to fine-tune the large language model further so that it can increase the efficiency of the model. So in ultimately they want to their objective is to improve the LLM's reasoning capabilities. Okay, so the second part is the same way they want to use reinforcement learning to increase the efficiency, one using a reward function design. So they're telling that we define a reward function based on passing the final recommendation output. A reward of 1 is assigned for correct predictions matching the ground truth, and minus 0.1 for incorrect prediction, and minus 1 for parsing failures. There were like some failures like parsing. Among the most, they are using the most prominent approach in reinforcement learning, which is called GRPO, Group Relative Policy Optimization. So there are other multiple methods which are like, which is PPO, DPO, and etc. But they're using the most like approach like which has been commonly used in the industry right now. So let's just quickly understand what is about supervised fine tuning and GRPO. For supervised fine tuning, they're kind of like using CLORA with 4-bit quantization. So kind of like this, we'll talk about what's CLORA and like how it will help us. And the second part is in the reinforcement learning, they're using something called GRPO, which is Group Relative Policy Optimization. So I've just taken a few slides from one of the University of Washington paper like deck. So which is like speaking about CLORA. So basically, when you have a large language model, you think about how vast and how big is the parameters in the large language model. If you just look at take a look at T5 model or a Mistral or a Llama 2 model, there are 11 billion parameters and 7 billion parameters and 70 billion parameters. Each of these large language model take up about 132 GB, 84 GB, and 840 GB of memory, while you need to like either inference or either to train. So if you need to fine tune, this is not easy. You need to have multiple GPUs with good amount of memory in it. So when you have for example, when you have this large language model which has to be which you want to use on domain specific data, you can't fine tune all of these parameters at once, which is either 11 billion or 7 billion or 70 billion. So for that reason, I think so one of the approaches what we use is supervised fine tuning, and one of the approaches in SFT is CLORA, and before this we call it as quantized low rank adaptation. So what we're talking here is CLORA reduces the memory for fine tuning by 15 to 20x. So if you see the same kind of like memory is being reduced when you use CLORA has the same thing with 6 GB, 132 GB to 6 GB, 84 GB to 5 GB, and 840 GB to 46 GB. We are efficiently using only a part of the, we're not using the entire 11 billion parameters, but we are kind of like utilizing another low rank kind of a matrix, which kind of like captures the new patterns in the fine tuning data, but also utilizing a very small part of the memory. So how does it do that basically is, so if you see on the left side is the regular fine tuning. So this has like inputs and the final output are embeddings edge. So when we have the new kind of like the samples which we want to like fine tune, so we have this pre-trained weights which is like the basic model basically, and if we pre-train if we kind of like fine tune it with the new samples what we get, and we want to fine tune the domain specific samples, we need to update the parameters of weight updates delta w, and this delta w happens to, for example, if we go to T5 it's 11 billion, and if we go to Mistral it's about like the same, it's about like 7 billion. So all of the 7 billion parameters are needs to be updated through this weight update, which is very, again, like, for maybe you have only 100 samples of your fine-tuned data with very less amount of fine-tuned data, and you're kind of like trying to update 7 billion parameters is a very inefficient method. So what happens in the LoRa, a part of it is basically the instead of like updating the whole pre-trained weights and the weight update for like the entire base version of the model, we kind of like introduce two matrices called matrix A and matrix B. And if we consider this weight matrix, like the pre-trained weights W is of the dimension like D cross D, we kind of like introduce these two matrices, which is like either by D cross R and R cross D, which we are bringing down into a very low dimension of the rank R. So this kind of like acts like reducing the number of parameters to kind of like update. Instead of updating D cross D, we're updating D cross R, and usually this R is less than 100. So around, like, if you tell 16, basically it will be like D cross 16 and 16 cross D is what the number of parameters you need to update. So this kind of like brings down the amount of parameters to update, and it's a small matrix. And what we can think about here is the LoRa weight changes plus the model update, model weights, the weight changes here, and the model weights is equal to the fine-tuned model weights, basically. So this is the simple low rank adaptation. So again, how it works is basically the input, what was going to the pre-trained weights also goes to the B and A matrix, and the output of BA matrix is added to the pre-trained weights while the fine-tuning is being done. So it kind of like adjusts towards the, when you're training the fine-tuning the model, it kind of like these BA matrices captures the projections and the intrinsic updates what needs to be done for the like the base model weights. So it kind of like helps in like fine tuning with a lot more lesser parameters. So now the same low rank adaptation with lot more lesser parameters, we kind of like for that is LoRa, but for Clora it's kind of like quantized low rank adaptation. So all of these weight matrices are of the precision of about FP 16, floating point 16 or floating point 32. So what we so we can either, as we know, quantization kind of like helps bring down the memory size. So one part of it is to quantization, and one what we can use is use int 4 quantization. So we can bring down the full floating point 16 to floating point 32 to integer 4 by using quantization bins. So once we bring down, for sure we know that from when we started, if we used to do full fine tuning, a 70 billion model would have taken 36 consumer GPUs. The same thing when we use just low rank adaptation matrices, the 17 billion model would just use 8x consumer GPUs, because we're only working on a few portion of the parameters and not the entire 70 billion parameters. And Clora, again, since we have been bringing down those model weights from either like a floating point 13 or 16 to a 4-bit int quantized model, so it just takes 2x consumer GPUs to fine tune the model, but with a very little less loss of accuracy as well. So that's the whole reason why Clora is a good way to like fine tune it with a lot more lesser computational power. But now coming to what is GRPO. So GRPO is group relative policy optimization. So given what it basically tells us, so basically is given a model state action, kind of like given a model, we kind of like take G responses of the model. So G responses is like, okay, so for GRPO is group relative policy optimization. So this is comes under the reinforcement learning, one of the techniques in reinforcement learning. It is based on of another algorithm called proximal policy optimization, but it's like the major difference between the proximal PPO and GRPO is proximal policy optimization as a critic model, which is like a really big model which needs a lot of computational power to actually fine tune, like give rewards to the to the policy updates. But in GRPO it's not that case. So basically here it's like we kind of like use the current policy to generate G responses, and then see how these responses are based like relatively between each other, and give out advantage, like give a more advantage and give a lot more kind of like give a lot more rewards to the ones which are really the responses which are really good, and the responses which are bad are given lower rewards. So to go through it, like you can just check, see this first part of it, where we have given a query, sample G responses from the same policy. So let's take the question to be like an equation, like finding the solution to an equation. So there may be three different responses for that given that equation. So if you see for the same equation, we got one correct answer, and the third response is the wrong answer. So the second part is to calculate the reward and advantages. So how do we do that? Is a reward is basically just giving 1 or 0. We know which is correct and which is wrong. So we can just tell, okay, first one is correct, second is correct, third one is wrong, so 1 1 0. So the third one is we calculate the advantage. So what does advantage tell you is, so if a policy like chose to do a particular action, like take a particular action, like take the action 1 or action 2 or action 3, what is the like how better is that action, instead of doing a random action out of the three. So kind of like relatively you kind of like figure out, like if I do action one, if I take action one, how is it better if I just randomly do one of these actions in random. So like an advantage. So basically, so we kind of like the advantage formula is basically like compute mean reward, take the mean and standard deviation, and then compute advantage. So if you see A1 and A2 have a higher advantage and A3 has a very low advantage, so because like either A3, like the A3 is really low, so we kind of like calculate that. And now coming to GRPO's equation is, we need to calculate the loss function. The total loss function is given as the GRPO's loss function of theta minus beta and KL divergence of the policy with the current parameters to the policy of reference parameters, or we call it as like probability, instead of like the, not the policy but the probability distribution of the current parameters to the probability distribution of the reference parameters. So what is LGRPO? Okay, in this equation, beta is basically a hyperparameter which is figured out during the training process, the reinforcement learning. So it tells about how much penalty, like this is part of the penalty of how different is the probability distribution from now to the probability distribution of the base model. If it is too different, you kind of like apply penalty to it, and how much penalty to be applied is given by the beta parameter, which is again an hyperparameter. Now the left part of it is the loss function called GRPO, and again for that it is it. So it's kind of like, it's what is it? The equation tells you here is, it is 1 by G with the summation of all the outputs of the uh, probability, like generating tokens basically. Again, so it's kind of like 1 divided by a G, and summation of 1 G is the number of G responses. For every G, you kind of like sum and average the loss function. And for that, main part of the loss function is basically kind of like a minimizing scenario of a clipped, if of unclipped and a clipped portion of the formula. So what you're telling here is, the unclipped version is like what we're talking about is the probability distribution of the current output given a query and all the previous tokens, divided by the probability distribution of the whole policy, the previous policy, for this output given the query and the whole tokens, into the advantage of that particular high, which is like the first query, then you will get advantage of 0.70. If it's the second query, you'll get again 0.70. If it's the third query, you'll get minus 1.41. So it's the weighted advantage of the probability, like how much improvement is there in the probability distribution. On the clipped version, this is the unclipped version. So this can go anywhere. This can either go anywhere between a lot, like it's like completely, it has no bounds. But in the clipped version, it's kind of like the the probability distribution of the current policy divided by the probability distribution of the whole policy, kind of like it's between, it should be either between 1 minus c or 1 plus c. If it goes above that or below that, it automatically, we kind of like take 1 minus c or 1 plus c as a what do you say, loss function. And we again do a weighted multiplication on towards that particular loss function. So um, again here, so basically again, but after we find this loss function, we kind of like use this loss function to y- once we get this loss function, we kind of use this loss function to calculate our gradients and do a back propagation to update our weights. So again here, gradient computation, we use kind of like the gradient of L total, this one, with respect to theta, then update using an optimizer like an Adam optimizer to adjust theta. So using this, we kind of like come up with like the new version of the policy with more updated weights, so through like GRPO. Understood about like what's GRPO and what's supervised fine tuning using Clara. So let's start looking into how the experimental setup was approached by this paper. So the paper tells that the gold start items never appear in the user interaction within either the training or testing datasets, and serve exclusively as ground truth targets in the cold start evaluation set. So the training and testing set do not have any cold start items, so that there is no leakage in data. So then again, they are evaluating on two things. One is called recall at one for discovery and recall at one for any play. So what does discovery mean is, it's like those items or like movies which the user has never seen before, and for any play is like the user would have like kind of like it's the normal user playback behavior, so captures any type of user playback behavior basically. So now for that, the data all the construction of data is basically like sampling thousands of interactions from records within one day, um, and the SFT training set, we sampled 16,200 interactions after removing cold start items. Applying our reasoning methods produced 7,252 successful reasoning paths derived from both base reason and soft self-consistency method, which achieve optimal performance. So what they're talking about is, they're talking about three different models. One is called the direct track, one is called the base reason and fast reason. Direct track is something they're thinking of like like they're using an LLM by prompting to produce a final recommendation without any intermediate reasoning. So given like five movies the user has watched, they're using the LLM to like given a candidate list, figure out which movie the user would watch just using prompting. So that's like the plain vanilla baseline. Second, base reason is basically guiding the LLM through a two-step process. First, reasoning about the preferences. Given that five movies which the user has watched, generate the reasoning or like common patterns the users would have watched, like a step-by-step thinking, and then out of the candidate list, figure out which movie the user would watch. With the second step, reasoning about preference towards candidate item based on a summary to generate the final recommendation. So the third one is fast reason. Fast reason talks about like builds on base reason by doubling the maximum interaction length. Maybe instead of using just five movies before, it starts using 15 movies before, increasing the number of historical data interactions it sees, while simplifying the reasoning process. So, but instead of using like a 5 to 6 step-by-step thinking process, it would have used only two-step thinking process, and also by giving instead of doing few shot, only giving one shot learning. So by looking into all of this, so they're using Quen 2.5 32 billion instruct as a model, and the base LLM has a base LLM basically. So what they see is basically the base reason outperforms direct tech on both metrics. The base reason where kind of like using like the step by step process thinking outperforms the direct rec, which is the direct recommendation, which is the baseline, and in both the metrics, in both NEP and discovery. So the same thing, the basis and fashion further shows that extending historical context while simplifying demonstrative pattern yields a substantial 23% gain in discovery, though the cost of reduced NEP performance. Structural reasoning, the more complex approach, improves NEP by decreases discovery by 6.4%. But in the end, the finding suggests that complex reasoning strategy, which requires LM to extract and analyze structural information, may enhance modeling of general user behavior but risk imbalanced performances across metrics. So simple approaches that grant greater flexibility in reasoning, giving it complete flexibility to generate the reasoning paths according to itself, gives a lot more efficient way, a lot more better way of capturing patterns and appear to achieve more balanced outcomes. So that's the reason, which is the soft self consistency approach. Now they're going to use these like again in supervised fine tuning. They're using Clora with 4-bit quantization. So they're going to take out those recommendations from both base season and soft self consistency to serve as training data, and they're going to train this model by only one epoch, by single epoch, and this is enhancing the generalizability or diversity in the training corpus. So this will and prevent future overfitting. And the same way in reinforcement learning, they're using GRPO to like train the model, and in the end, what do they see is the improvement margin of SFT plus GRP over the baseline is 8% higher than that of the Netflix production model on the discovery metric. Even though the Netflix production model has been like trained on millions of interactions, so just training on a few samples of just a day's interactions improves the discovery metric of again, this is not like completely cold start, but it's a warm start setting where it's kind of like increasing the discovery for. So there are a lot of things which are like very questionable in this paper, but just like taking out looking just a few patterns in it talks about like generating reasoning paths as a unique way of like understanding user preferences, and bringing LLM to generate these reasoning paths bring a lot more world knowledge and get out the user intent understanding and user behavioral understanding a lot more better. And using these, we can actually generate a lot more better recommendation models, either in session recommendation models or kind of like even as well as cold start scenarios. So maybe one quick one takeaway from this paper I would take away is the reasoning part. I would use this output of the reasoning part to better build more better embedding and user embeddings or item embeddings or any candidate embeddings, and then kind of like use like a two tower model to kind of like get the appropriate